Welcome everybody, this is Yasser Wasifi again from Learn Dental Series. Today we will discuss the topic of composite resin restoration as an example of direct tooth color restoration. First of all, I would like to declare that I don't receive fees, compensation or royalties from the sales of any of the products shown or discussed. Also, I declare that I haven't any conflict of interest with any of the discussed products or technique. Also, I would like to announce that this presentation is copyright protected and no part of it could be used or transmitted by any means unless you get a written permission of me. Our objective today is to select the most suitable type of composite restorative material for our case or to repair our defect. That's why it will allow us to reproduce perfectly the tooth anatomical, functional, and aesthetic form using composite material. And we would like to highlight how to manage the shortcomings of composite resin and get the best result of the material. This is by following all acceptable clinical protocols and techniques to increase the prognosis and success rate and the clinical serviceability of our composite resin material. Our topic will be classified into three parts. The first part was concerned with the material itself and the material review, which will be the longest part. Then tooth preparation and finally manipulation of the material. Let us start with the material review with the history and the development. And in this article titled Significant Events in the History of Operative Dentistry, published in the Journal of History of Dentistry in 2005. The story started as early as the 1st century by Celsius, who recommended the mended lint with lead to be used to fill the anterior teeth cavities. Then alum mixed with honey and ground mesquite in the Mediterranean area. Then 500 years ago, gold foil introduced to the restorative choices for anterior teeth, as at this time golden metallic appearance was considered as the most acceptable aesthetic and luxury appearance. In 1855, Robert Arthur heated gold foil to make it much more cohesive, until in 1878 Fletcher introduced silicate cement in England and Europe, then used in the United States in 1908. Silicate cement have a fluoride releasing capacity, but its solubility in oral fluid was high, which threatened its longevity as a restoration. And due to it is the first tooth colored, or it takes the tooth color, it is considered as a tooth colored restoration. Restorations of silicate cement continue to be used as a direct restorative material, static restorative material, or a direct tooth color to be definite up to the 70s of the 20th century. Even Gilmore, which is an iconic scientist in operative dentistry, in 1967, he thought that nothing could threaten the throne of silicate cement as direct tooth colored restorative material. But self-cured acrylic resin developed in late 30s, okay, and in late 40s it is used as direct tooth colored restorative material, but its color stability and serviceability, although it's much higher than silicate cement, but it is not common or famous as silicate cement because of its marginal leakage as a result of great difference in coefficient of cerebral expansion and contraction, and due to great amount of volumetric shrinkage upon polymerization. In 1958, it started with Raphael Bone, a general dentist, who added silica to the acrylic resin and made it termed filled resin. And this is the exact correct scientific terminology of composite resin. That's why I focus and stress on that. Composite is not a name of a material. Composite is a character of ultrastructure of material, means the material is heterogeneous. That's why amalgam could be termed as a composite material, because it is a multi-phase in ultrastructure and it is heterogeneous in structure. That's why it is composite. So the correct terminology is either you termed it as composite resin or resin composite, or the best is to term it as filled resin. In 1973, ultraviolet light curing was introduced, and in 1978, visible light cured replaced the ultraviolet curing in order to overcome its uh, negative effect or its hazardous effect on the eyes of the operator and of the patient. This is Raphael Bohn, who was born in 1925 and passed away in 2018. He is, as this is his CV, as published in the website of American Dental Association. He gets his DDS degree as a general dentist in 1953 and his doctorate degree in 1987. Okay, he was just a GB who would like to improve the properties and the clinical longevity and serviceability of acrylic resin and just added silica as a filler to improve it. Raphael Bohn only participated in 15 articles or in 15 research papers from more than 1 billion researchers considering his innovation of composite resin material. Most of his papers or researches was as a co-investigator with Hussein Latif. Okay, it's just only 15, and his role was as a co-investigator. This is one of the last projects he had published in 2014, and he is a co-investigator, and the last one was published after he passed away in 2018, and also he was as a co-investigator. This is the timeline describing the development of composite resin material. It all started in 1958, the original development. Then macrofill composite was introduced in early 60s. At this time, the composite was unbonded. No bonding agent was used at this time. Okay, the idea of bonding to two structure was not yet developed. Then acid etching was developed and introduced to the clinical practice in early 70s. At this time, Medifill composite also was developed. Then at late 70s, microfilled composite, dentine bonding agent to composite or bonding to dentine as a concept of dentine, as a concept of dentine bonding in early 80s. Okay, at this time, Medifill was developed in the mid 80s and Medi-hybrid in the late 80s. Then from the late 80s till now, dentine bonding agent with the concept of dentine hybridization was developed and was used in routine daily practice of restorative dentistry. Either it is 3 components, 2 components, and now we are using 1 component systems. In the late 90s, flowable and backable systems were developed, followed by many hybrid, then controlled shrinkage in the early 2000s. Okay, then comes nano hybrid composite, nanofill composite in 2005, and self-adhering flowable in the early 10th, and bulk fill composite about 2014, icon resin infiltration in 2015, okay, smart chromatic composite in 2019, and we don't know what comes tomorrow, because the continuous refinement and the improvement of the material to counteract the technique sensitivity and to improve its properties is continuous over a time, and we don't know when it will stop. Okay, for the early composite materials, it was chemical self-cured composites, then comes the ultraviolet chemical cured composite, but now from the mid 80s up till now, we are using visible light cured composite using quartz tungsten halogen devices or plasma arc or laser or light emitting diodes. Those written in green are the most commonly used or commercially available now. When we could discuss when we would like to discuss the types of aesthetic restorative materials, it all, as we mentioned, started with silicate cement, which is acid-soluble glass or silica and alumina powders with calcium fluoride and sodium aluminum fluoridated fine traces of arsenic with the liquid of 35 to 50% phosphoric acid. Its advantage was the highly translucent, high color match and carcinogenicity due to fluoride, but actually its shortcomings was its high solubility in oral fluids, discoloration and loss of contour, but what is most important and what is most dangerous, its effect on the bulb due to its arsenic content, which made it termed as painless bulb killer. Then comes the acrylic resin with the composition of polymethyl methacrylate and benzoyl peroxide initiator with inert coloring agent with a liquid of methyl methacrylate monomer with tertiary amine activator and hydroquinone inhibitor. It's like any other acrylic resin material, having a good initial aesthetic and the color, and with the advantage over that of the silicate cement, it is insoluble or in oral fluid, but due to water absorption, due to its great amount of volumetric polymerization shrinkage, and also its coefficient of thermal expansion and contraction is 7 times more, double that of the tooth structure. It shows lack of color stability, low strength, polymerization shrinkage, and the coefficient of thermal expansion is higher than that of tooth structure. Then composite resin, as we mentioned, was introduced by Raphael Bohn by adding silica as a filler to our material, and this will be our topic, our target from this presentation. Then glass ionomer is introduced in a conventional form by Wilson and Kennett in 1972 with the advantage of having fluoride release, okay, but sensitive to moisture and could not be finished immediately. That's why it is modified into resin modified GIC to improve its technique sensitivity and improving its physical properties, but it adversely or negatively affects its fluoride release. Then a combination between composite and amalgam was introduced, which was polyacid modified composite or compoveneers. Ceramic and inlays and overlays was another innovation, producing a highly aesthetic and a better color matching, okay, for or color shade matching for that of the tooth structure. Either it is man-made or using the new technologies of CAD/CAM, 3D printing, and other computerized or digital technologies. Okay, let us start to discuss in details and discuss the rationale or clinical rationale of the chemistry of composite resin. Composite resin composed mainly of 3 basic phases. Phase 1, which is the matrix phase, which is the organic resin, the original organic resin. Then comes the dispersed phase or inorganic filler, which is added, which is the silica added by Raphael Bohn to improve the properties of the material, and coupling phase, silane coupling agent to bind between the organic and the inorganic phases of the material. Considering the matrix phase, it is the resonance component. It is responsible for the setting reaction. This is the part which undergoes reaction and produce setting and let the material harden. That was why it is the part responsible for the amount of polymerization shrinkage. When it shrink or when it harden, it holds or it grabs your filler particle. Okay, that's why it is responsible for holding the dispersed phase, which is the filler. It is responsible for the high difference in coefficient of thermal expansion and contraction. It is the part which undergoes water absorption. It is the part with the color ingredients. That's why it is responsible for color stability and responsible for low strength. Our matrix phase composed of at least 5 basic ingredients, which is the monomer system, diluent, activator, initiator system, inhibitor, color modifier, and stabilizer. Let us discuss the monomer system, which is an oligomer of 2 monomer system, namely bis-GMA, which is the acronym of alpha bisphenol glycidyl methacrylate. Please don't term it bis-gamma. Okay, it's bis GMA, because each letter is referred to a material or a compound. It's alpha bisphenol glycidyl methacrylate with urethane dimethacrylate. This is the oligomer we used. We used also, or we add also a diluent to control viscosity. Why? Because when you add a filler to your monomer system, the viscosity increased and the material becomes with low wetting. It becomes a very tough dough that has limited wetting that will affect your adaptation to cavity walls and margins. That's why it is important to add a diluent to control your viscosity, and the most common one is triethylene glycol dimethacrylate. The question comes to our mind is, it is originally acrylic resin. Why we don't use methyl methacrylate? We use bisphenol glycidyl methacrylate. What is the difference? In this diagram, we could illustrate the difference. Methyl methacrylate having a low molecular weight molecules with very short molecules, while bis GMA is higher molecular weight with longer molecules. When they undergo cross-linking or undergo polymerization and united to each other, please note with us what happens to methyl methacrylate. Okay, it develops a polymerization shrinkage to that amount, while the long molecules will produce a lesser polymerization shrinkage. And this is considered as the first idea or the first step in controlling polymerization shrinkage of the material by changing the type of monomer using another oligomer with high molecular weight. When it binds to each other, okay, there will no great amount of volumetric shrinkage. Okay, then come the activator and the initiator system. Activator and the initiator system, when you thinking about binding short molecules with each other to form larger one, which is the polymerization reaction, okay, which is considered as bonding simple short chains molecules, which is a monomer, to form more complex, compact, strong, long chains molecules. You need ties to tie these short molecules with each other, which is the free radicals. From where could you get the free radicals? You need a material which easily decomposed, releasing these free radicals to allow this linking, which is the initiator. But this initiator requires activator to decompose it to release the free radicals. That's why for proper or for the polymerization reaction to start, you need an initiator to be decomposed to allow cross-linking by releasing free radicals. But this initiator in turn in need for activator to break it down to release the free radicals. If you notice, our example is a matchbox. Okay, this part of matchbox in which you press your match against it to produce friction. This produces the first frictional heat and considered as the activator, which is responsible to decompose the head of your matchstick, okay, which is easily weak compound, which is easily decomposed by the least frictional heat and start your reaction, start the burn. Okay, this is considered as the initiator. Okay, at the same time, this is the wooden stick which will continue the burn due to effect of initiator. But please note something. The much more you decompose the initiator head, the more will be the lightening of the wooden stick. Okay, the same will be for polymerization reaction. The much more you decompose your initiator with the activator, the more will be the produced free radicals, the more will be the cross-linking, and the better will be the properties of the material. Okay, that's the same like your matchsticks. Okay, the more decomposition of the initiator head, the more will be the burn that will affect and burn the whole stick or the whole wooden stick. Okay, and the more will be the lightening. But if you notice the last one, or the difference between one from another is while the degree of burning that produces much more lightning increased, there is also a dimensional changes in relation to it. That means that the more decomposition of the initiator head, the more the burning will occur, the more the lightning you will get from this matchstick, and at the same time, the more will be the dimensional changes or shrinkage. It is the same for composite resin material. The more the activator decomposes the initiator, the more will be the released free radicals, the more will be the conversion from monomer to polymer and cross-linking. This will affect the final properties of the material positively, but at the same time will result in much more and more volumetric shrinkage of the material. Then, polymerization shrinkage. Okay, let me clarify this because it is very important. Polymerization shrinkage is an important positive criteria for your polymerization reaction. By that means, or that's to say, when you get maximum polymerization shrinkage, means that you maximally cross-tying your polymer chains, and the material will get the best mechanical and physical properties in terms of strength, in terms of modulus of elasticity and stiffness, and all mechanical properties are improved. Okay, but the problem is, or the question is, does this polymerization shrinkage takes place inside your prepared cavity? This is the problem, because you already place the material while it is not yet polymerized, okay, and it undergoes its polymerization reaction inside your cavity, and this shrinkage takes place inside the cavity. This is the problem. The problem actually is this shrinkage. Although it is a positive sign that you get the maximum properties of your material, but the problem is it takes place inside your cavity and jeopardize your adaptation, okay, and the material is separated from the cavity wall and creating a gap. This is the problem. And all over this chapter, and by using different techniques, we will try to direct this shrinkage away from the interface between the tooth and the restoration. Okay, there is no composite without polymerization shrinkage. Okay, because no shrinkage means no polymerization, means that this is not a material, it's a dough placed inside the cavity. Okay, but the game is how to direct this polymerization shrinkage away from the interface between the tooth structure or the cavity wall and the material. Okay, but actually, as long as you get maximum shrinkage, that means that you get maximum conversion, you mean that your polymerization reaction goes forward to the end, okay, and you will get a material with maximum properties. Okay, also activator could be by any other means rather than your activation system of matching box. Okay, it may be you may burn or lighten your match from another source, okay, or another hot source. The same for our composite, it is either chemically activated or photolight activated. What is the difference? Chemically activated, having a chemical activator material and an initiator separated, each one in a separate container. That's why it comes into two base system, one of them containing the activator and one of them containing the initiator. Once they touches each other, activator will decompose the initiator and the reaction starts. Okay, while the other one is using light waves or energy taken from light radiation, okay, where it breaks the light energy in joules, breaks down initiator, special initiator, to produce the free radicals. Okay. Another difference regarding the polymerization shrinkage and its direction. Okay. Composite starts the reaction at the site of maximum initiation or at the site starting the initiation. For chemical cured, once you mixed them, the maximum initiation will be in the center of the material, while for light activated one, the first site to be initiated is near to that of the light. That's why chemical cured shrink towards the center, where it is the site of first initiation and maximum initiation, while for light activated, your composite will shrink towards the light where the first initiation and the maximum initiation occurs. That's why we could use those properties for chemical and for light activated in advantage for us as a clinician. Okay, chemically activated, as we mentioned now, because it is a chemical activator decomposing a chemical initiator, you should separate them, and that's why it comes in two based system in two different containers. Okay, once you are mixing them, the reaction starts. What is the benefits of this? The benefits that your reaction will be homogeneous, your reaction will be maximum, because the reaction will not stop until all the activator is decomposing all the initiator and all the released free radicals are used. Okay? This is the advantage. But the disadvantage is when you are mixing them together. Okay, once you say mixing, then there will be an entrapped air which will affect the strength properties, okay, of the final strength properties of the material due to these entrapped air voids, okay, and at the same time it will negatively affect the aesthetic result of your restoration. Okay, another disadvantage is the direction of polymerization, which is towards the center, and as you could notice, it will be away from the cavity walls or from the interface and leads to formation of gap between restoration and the tooth. Okay, that's why you may imagine or you may thought it is not produced nowadays, it is not indicated, it is not used. No, this is not true. Still it is produced, still it is manufactured and marketed, but for a core build up around a post in endodontically treated teeth. Why? Because it shrinks towards the center, okay, where the center contains the post, then it will produce maximum adaptation around this post. Okay, what about the aesthetic quality? I'm not in need for this aesthetic quality because it's a core material and it will be coverage by a full coverage restoration. Okay, for photo initiated one, the advantage is unlimited working time, okay, because it will not start sitting unless you exposed it to light. Okay, that's why it is termed a command sitting by order. Once you order it by the light to start sitting, okay, it will start sitting. When the reaction stops, once you switch off your light, the reaction stops. That's why its polymerization reaction is to somehow unhomogeneous, as it is affected by the power of light in terms of wavelengths and time. Okay, and also affected by the thickness of the material, because your light will attenuate, okay, when it goes far to the thickness, and the researchers proved that you need maximum 2 millimeter thickness of your material. More than 2 millimeter will not be affected by the light activation, and the material will not undergo polymerization reaction. Okay, also we could benefit from the direction of light by bringing the light from the same direction of cavity walls. That's why it will be directed or it will be attracted towards the wall, okay, rather than away from the wall, which will be discussed under the terminology of guided polymerization. Okay, this is what is photo initiated and chemically initiated. But remember also that your material, which is the photoactivated one, is sensitive to ambient light. Okay? Actually, it will not be cured or will not start reaction, okay, unless you expose it to your device of light curing. But actually, it will absorb a little bit amount of ambient light time by time, okay. You repeated its use without recapping the tube, it will absorb a cumulative amount of light energy that will affect its shelf life and may decompose or self-decompose, and the material will set. Okay, this is a brief comparison between chemically activated and light activated. Chemically activated with activator tertiary aromatic amine and the initiator benzoyl peroxide, and no need for light absorber, and it comes in two base system with you mix equal amount of each component, and as we said, mix, then there will be an entrapped air. Light activated, which is activated either by ultraviolet, which is not used nowadays or no longer used, visible light in a wavelength ranged between 460 and 480 nanometers. With initiator camphoquinone, you have to add light absorber to fasten the reaction, okay, to get exposed only in 20 seconds, not in 20 minutes, okay. Benzoyl methyl ether for ultraviolet, which is nowadays no longer used because already we no longer use ultraviolet, okay. Alpha diketone, which is aliphatic amine for visible light cured, comes in one base system and the material is readily available. Working time for chemically activated is limited, but it adds an advantage that its setting reaction started upon mixing. Okay, this is a disadvantage because it limits your working time, but it extended until complete consumption of initiator free radicals had taken place. That's why its conversion rate is homogeneous with maximum curing, although the color and shade are poor quality because of the voids, okay, and working time limitation and moisture are considered as the main cause of technique sensitivity. For light activated, the working time is flexible, okay. The setting is command, just start when you expose it to light and extended until light emission stops. That's why one of its disadvantages is unhomogeneous conversion, which is affected by time and depth of light emission, which is characterized or defined as to be maximum 2 millimeter increment, but the color and shade is of high quality. Its technique sensitivity for sensitive to ambient light, and also as all composites and all restorative materials by in term, okay, with sensitive to moisture and sunlight. This is the two components or two base system of chemically activated, and this is the photo initiated one. This diagrams illustrates to you how the setting reaction and the conversion of light activated material is affected by the depths of light exposure or light transmitted into your increment, okay. You could note that it is of reasonable result only at 2 millimeter thickness as maximum, but more than 2 millimeter thickness, your conversion rate will be very bad, okay, and the material will not undergo setting. This illustration shows to us that we are working in the blue light zone of the visible light, okay. This is the blue zone, which is with a range of 46 up to 48 nanometer, okay, because at this range the energy in 20 seconds could decompose our camphoquinone initiator, okay. But there is an important issue. We have many devices, mostly now the commercially available devices is quartz tungsten halogen, okay, with halogen lamp or light emitting diode, okay. you should note that your camphoquinone needs a light energy or a photo energy in the range of 460 up to 480. Any excess unused irradiation will be transformed into heat, and this is a problem, okay, that by time will affect the power and the irradiation released from your device or from your lamp. At this graph, okay, you could note that the camphoquinone in yellow, this is the range of camphoquinone, okay, lead in red, and quartz tungsten halogen in blue, the blue one, okay. Quartz tungsten halogen have a wider spectrum where you used only a narrow one for to decompose camphoquinone, and the other will be transformed, the excess radiation will be transformed into heat. That's why when you are working with quartz tungsten halogen device, okay, this device will be supplied with internal fan just to cool the heat produced by extra unused waves, okay, or wave spectrum, wavelengths, okay. That's why in order to increase the lifespan of your device, please don't switch off your device. You only press to stop your emission of light, but don't switch off your your device unless the fan stopped. As long as you hear that your fan is working, please don't switch off your device, otherwise the latent heat will damage your lamp, and your lamp will not release time by time, or not release the required wavelengths for curing your composite. And that's why when you used all the device, okay, please increase the time to compensate for the lowest output of your wavelengths of your device, okay. This is not true for light emitting diode. That's why light emitting diode is highly efficient than quartz tungsten halogen, but this does not mean that quartz tungsten halogen is contraindicated, but nowadays it is limitedly marketed and limitedly available in the market. That's why you should take a note that the maximum consumption again of initiator free radicals, okay, the higher will be the degree of conversion of composite, the better will be surface and mechanical properties of the composite, the higher will be the wear resistance, and at the same time the higher will be the volumetric polymerization shrinkage. What is meant by degree of conversion? Is it equal to degree of polymerization? No. Degree of conversion is a chemical terminology describing what happens to your monomer chain to be converted into polymer chain. Your monomer is composed of carbon atoms which binds to each other with carbon double bond. When it binds to another molecule, then it will replace one of these double bonds and bind to the other molecule, and then it comes from it gets converted from carbon double bond to carbon single bond. And the degree of conversion is the extent to which the carbon double bond length, okay, is converted into carbon single bond. Okay, I think it's vague, it's difficult to understand, but let us review this clip, okay. Considering the polymerization process of polyethylene, polyethylene is used as a stretching wrapping material for groceries, and at the same time drainage pipes, which is extremely hard, okay, could be or is manufactured also from polyethylene. This is the ethylene molecule, two carbons with carbon double bond. This is the peroxide initiator, which is activated by heat. Activation heat is heat, which already splits the initiator, okay, producing free radicals that would like to be stable. Then it will take one of the bonds, okay, of carbon double bonds, and the outer molecule will be unstable until it take another bond with the other one, okay, and the process continues, and this is what is called propagation. This is how the initiator starts a polymerization reaction, and this is the propagation. Just to make all molecules stable, it should bind with each other, especially carbon atoms binds with 4 bonds, okay, until the end of one chain bind to the end of another chain, okay, and this is the termination. You could note that there is a continuous initiation by heat for your initiator. Then come the cross-linking process, okay, with the continuous decomposition of your initiator by heat. Free radicals will continue to be produced. Those are the polymer chains, but how to cross tie them? This is a continuous decomposition of initiator, but this time will not find a carbon bond to bond with it. It will take a hydrogen ion from it, leaving this bond, okay, to bond between two molecules in different chains. This is the cross-linking. And according to the amount of cross-linking, the physical properties of the material and the stability of the material, okay, will differ. Either it will be stretchable, okay, or it will be stiff and rigid enough, okay, stretchable to make the stretch wrapping, or stiff enough to make the pipe tubes, okay. This is a brief description of the conversion, but the material may, from room temperature, okay, self-decompose. That's why you should add an inhibitor in a form of butylated hydroxytoluene or monomethyl ether of hydroquinone, which is called methanol, okay, is added in a very small amount to decrease self-polymerization and increase the shelf life of the material. But you should note something important, okay? When you expose the surface of the material to outer air, okay, it combines with oxygen and creating what is called oxygen-inhibited polymerization layer. Oxygen inhibits polymerization, okay. When you leave your tube opened, unclosed, okay, it may be at this time bind to oxygen and create oxygen-inhibited layer, or it may absorb light from the ambient light, okay, leading to cumulative absorption of light energy at the required wavelengths until you find it starting to set. That's why it is recommended to cap it, or instructed to cap the composite resin tube immediately after you get the amount you needed, okay. If you have a tube which is uncommonly used for a long time, okay, it should be refrigerated, not frozen, refrigerated. Why refrigerated? To inhibit the self-decomposition effect, okay. And when you would like to use it, just get it out of the refrigerator about 1 hour, just to become in room temperature. Otherwise you will be in need to increase your curing time to compensate for this delayed initiation, okay. And it is preferable to squeeze 1 to 1.5 milli slice and slice it and discard it out, because this first slice is either oxygen inhibited or either started to be affected by the ambient light. Then color modifiers and the stabilizer are added, okay, to give a variety of composite shades to match your tooth structure. Then comes the dispersed phase, which is the filler added by Raphael Bone. This is the innovation of Raphael Bone. The other is other component was matrix phase, which is organic resin, and this is the inorganic filler added by Raphael Bone. It decreases the total amount of resin used, okay. That's why it improves aesthetics by being silica derivatives, by adding translucency, reduce water absorption, okay. At the same time, it improves physical properties because you already reduce the amount of resin, okay, and substitute it by filler. Okay, it reduces water absorption, reduce polymerization, shrinkage, reduce coefficient of thermal expansion, and increase hardness. And also, it improves all the mechanical properties in terms of compressive, tensile strength, stiffness, and abrasion resistance. Okay, you should note that the greater the amount of filler, the less will be the resin matrix available, and all the shortcomings related to the resin matrix will be decreased. That's why it will be the material will be of better physical properties and mechanical properties. But at the same time, the higher will be the viscosity with lower wetting and adaptation. That's why you are in need to add dilute. Types of filler are variable. The old traditional one is crystalline quartz, then silica glass, then nanoparticles of silica and zirconia. Okay, and all manufacturers have different types of fillers, may be combination of all of these filler, but what is important is the filler size and distribution. According to Bine and Heyman, filler may be megafilled, okay, which is referred as insert, okay, of diameter ranged from 0.5 to 2 millimeters. Macrofill, which is added by Raphael Bone, ranged from 10 to 100 micron, not used anymore. Medifill, 1 to 10 microns. Minifill, 0.1 to 1 micron. Microfill, 0.01 to 0.1 micron, which is recommended to be used for class 3 and class 5 restorations where it is a non-stress bearing area. Then comes nanofill composite, which is ranged between 0.005 to 0.1 micron of non-silicate based compositions which are below the wavelengths of visible light. That's why it has an improved translucency and shade matching. Okay, then comes a group of hybrid, okay, which is a mix between two types to get a blended properties or bended properties. Hybrid is a combination of macro and micro, midi and micro, mini and micro, and nano hybrid, which is mini and nanofill. Why you are going to produce or going to add different sizes in a form of hybrid filler? The larger the filler particles, the better will be the mechanical and strength properties. Okay, but at the same time, the negatively will be affected, okay, the aesthetic quality of your restoration. Okay, decreasing the filler particle increase its ability to polishability and smoothing, increase its translucency, but the material will become with vulnerable, okay, or questionable strength properties. That's why comes the idea of hybridization, okay, to add large and small particles to get the benefits of two of them. Why the large particles are aesthetically unacceptable, while it is a large silica particle, okay, which is translucent like glass, okay, because there is no bond between the resin and between the filler. When you are going to finish your restoration or under occlusal loading force, any abrasive activity at the surface will get your filler particle, extracting it out of the mix of the material, leaving a rough surface. That's why when you are using a very fine particles, it produces a minute, invisible, unseen irregularities, okay, and will produce much better surface smoothing and polishability. Okay, that's why we are blending between two types, large and smaller one, okay, in different forms and called the hybrid ones. Okay, this diagram showing you how we mix it. Okay, micro with macro. This was the first hybrid. Okay, then midi with micro. This is the second hybrid or midi hybrid. Then comes mini with micro, mini hybrid, and nano with mini. This is the nano hybrid. This is our ruler, to discuss the difference ranging from 1 millimeter to 1 angstrom. 1 micron is the dental standard reference. Okay, dentinal tubules are a little bit larger than 1 micron. Bacteria is about 1 micron, microorganism, and atomic dimension is angstrom, is measured in angstrom, and 0.1 micron is the IBS target for wear resistance. Okay, those are the different sizes of our fillers: mega fill, okay, macro, midi, mini, micro, and nano filler. When you blend macro with micro, this is the first hybrid. Then comes midi with micro, midi hybrid. Mini with micro is mini hybrid, and mini with nano is the nano hybrid, which is located at this region. And this is finally the true nano one. Okay, this is a scanning electron microscope showing the difference between filler sizes of macro, micro, and hybrid. Okay, this is the nano fillers, which may be in a form of either nano cluster or true nano. Nano cluster, you are joining or pressing a group of nano fillers to be in a form of 1 micron, and it constitutes about microfilled ones. Okay, this one in the upper is considered as a micro one, which inside it, okay, or composed of a group of nano, and that's why it is called nano cluster, and this is the true nano one. What is the difference between all of these sizes? If you consider these discs of composite are of the same shade, okay, and of the same thickness, hybrid is different than micro, is different than nano composite in translucency, okay, and this adds to your shade matching, and this adds to your aesthetic reproduction. This is the difference, as we mentioned before, between large particles and small particles in case of you are finishing, and the finishability, polishability with smoothing of your surface. Okay. This is the scanning electron microscope showing the difference between small particles and large particles in the finished surface. Also, fillers may be homogeneous or may be heterogeneous. Homogeneous is the regular one, which is a composite of organic matrix and a filler. But heterogeneous one, part of its filler is a pre-polymerized composite of the same time, okay, crushed and grinded, okay, to be a filler in your composite. Okay, then you have two types of fillers: the original inorganic filler and the pre-polymerized composite as an additive filler. It is also another trial from the manufacturer to reduce the polymerization shrinkage. This schematic diagram is popular, that showing the difference between homogeneous and heterogeneous, the difference between different types and sizes, and the hybrid ones. Okay, please note that the filler size always determines the surface smoothing and translucency. Okay, large particles produces a rougher opaque surface. Okay, and always composite is classified according to its filler size. Filler content affecting the resultant polymerization shrinkage. Okay, and as the filler content increases, total shrinkage will be decreased, hardness and abrasion resistance will be increased, wetting and adaptation will be decreased. That's why you are in need to add dilute. When you consider translucency, translucency is not only affected by the filler size, but all of these discs are the same material, the same shade, from the same tube of your composite. Okay, the difference is in the increment thickness. When the increment thickness increased, the translucency decreased. That's why most of manufacturers provide you with different shades for enamel and different shades of dentine when you are going to restore a huge cavity or an extensive cavity, in order to not using one shade, okay, that will appear opaque or loss of translucency due to increased thickness of the same one. This is the macrofill one, which is no longer used nowadays. Okay, microfill composites, which is used today, although it's still used, although its modulus of elasticity is lower, okay, than other regular composites. Okay, that's why it is the material recommended for restoring class 5 carious lesion, especially if the patient have cervical flexion due to stressful occlusion or parafunctional habits. Okay, that's why it is suitable to restore class 5 lesions in such a case, not only for its polishability and its smooth translucent surface, but also due to its low modulus of elasticity that allow it to flex with your tooth, and it will be discussed in full details later on. Hybrid composite, it is the one considered as universal one. Backable composite, it was a trial to get a composite with the feel of condensation like that of amalgam in order to easier restoration of proximal contact and give a similar handling properties to that of amalgam to prevent stiffness with the instrument and ensure proper restoration of contact. But actually, it is highly viscous. Okay, that's why it failed to achieve these goals, because it is highly viscous. That's why you are in need for other material that allows sufficient flow. Okay, that's why flowable composite was developed, and this system was composed of two consistency system: one flowable to act as a liner or a base with sufficient flow with low filler contents, which is the flowable one, okay, and the backable one to restore the tooth. Also, it was difficult to adapt layers to each other. It includes dry spots, okay, which is devoid from sufficient wetting of matrix, okay. It is more opaque, okay, and have larger filler particles that will lead to poor wear resistance. That's why it is no longer available or limitedly available now. While the other component of this system, which is a flowable composite with low filler content, is still used up till now as a liner, okay, or Betts and Fisher sealant, and at the same time, due to its low modulus of elasticity, it is similar to that of microfill. It is the material of choice for class 5 lesions. Nanofilled composite is extremely small particles which are away from smaller than the wave length of normal light. That's why it provides a higher translucency, higher aesthetic, at the same time with greater filler loading that provides high strength properties. But actually there is a problem with nano-filled composite when manufactured. It is better to be of nanocluster to add silane coupling agent perfectly. Okay, nano-hybrid composite is the newer version of hybrid composite, which is the most commonly used, but the problem that it may dull after a few years, okay, due to wear. Then comes one of the most important phases of the chemistry of amalgam, of the chemistry of composite, which is the silane coupling agent or coupling phase. It is the phase that join both filler and matrix together because they are chemically incompatible, one organic and one inorganic. Okay, that's why wear resistance will be decreased as there will be a stress transfer between the filler and the matrix, because this is the actual problem of wear of our composite, that there is no chemical bond between the filler and the matrix, and there is no stress transfer between them. Okay, that's why your resin matrix may be fractured, okay, leads to dislodgement of your filler particles and wearing of the surface. Okay, this is a schematic diagram showing the wear of the material. Okay, the material will look like the rice cake as you could see. Okay, this particles is the filler. Okay, and there is a breakdown of the matrix by time your filler will be washed away. Okay, this is another animated graph. This is the filler particles in yellow, okay, and resin matrix in green. When force applied, they are not bind to each other, okay, and no stress transfer from one to other. They are not strengthening each other. They are not sharing this force that will lead to cracks and the fracture of the weakest phase, which is the resin matrix phase, leading to dislodgement of the filler from its place and complete breakdown of the resonance matrix, leading to wear of the material. When you are using silane coupling agent, there will be an intermediate phase in between them, okay, leading to much more binding and much more stress transfer between two phases, and this will limit the wear of the material. This is a scanning electron micrograph of the wear of different surfaces of composite. Okay, you could note from the left one the dislodgement of filler particles. Okay, this is another magnification showing that how the filler could be dislodged due to weakening of the matrix or cracks of the matrix. You could note it in the right one, okay, leading to surface roughness. This is the composite. After 5 years, you could note how the surface is lost, okay. The material used is organosilane, which is bifunctional molecules, organic and inorganic, bonding between matrix and filler, improve mechanical properties and improve wear resistance. But you should note that the wear resistance of composite material is not only the responsibility of silane coupling agent. This is what your manufacturer added in order to counteract this effect, but also the degree of conversion, the water absorption, and the occlusal loading force is responsible for this. Okay, if your degree of conversion is not complete or your polymerization is incomplete, if the material is admiring water, and if the restoration is subjected to extraordinary occlusal stresses, all of these will also lead to wear of the material. Finally, those are the textbooks I used. Okay, remember that your question are welcomed anytime, either by commenting to this video or by sending to me an email, and I will reply to you as soon as possible. Finally, I would like to thank you for assigning your precious time to listen to me. Please don't forget to subscribe to my channel and activate notification to get all the new episodes in Operative Dentistry. Thank you, Yasser al-Wasifi.